talking about solving systems of equations by solution. This is section 4.2. And just to recap, we've already discussed systems of equations. It's two or more related equations that can be graphed on the same coordinate plane. Just related equations means they're equations that are talking about the same thing. They can be graphed on the same coordinate plane because the x variables and the y variables are describing the same item, right? They're both time and money, or they're both, time and distance. Whatever they are, the x in both equations is the same and the y in both equations is the same. So the solution to a system of equations then is the point where the graphs of the equations intersect. So for example, if we have a system of equations, it might look something like this. Two equations here. And the solution would be this point right here where the two lines cross each other. That is the solution. But it's important to remember that the solution is always represented by an ordered pair, right? There is an x value and a y value to the solution. You have to have both those numbers to represent the solution to the system of equations. Okay? This is what we've talked about so far, but sometimes, what if we had a system of equations where we just can't easily read the solution from a graph? And so here's, just a small example. I can see that there is a solution to this system of equations for sure, but what is that x value and what is that y value? That I can't tell. I can see the x is a little more than 1, the y is a little more than 1, but I'm not sure exactly what those numbers are. When this kind of a situation arises, we need to find another way. We need to find another method to solve so that we're not reliant simply on finding the exact numbers from a graph. So here is another system of equations that we can use for an example. And we can talk about how to solve these using substitution. Right? This is the other method that we're going to talk about today. So just like the name substitution would imply, it would help if I could spell it right, substitution. We're going to substitute a value in. I have two equations here, and I know from our definition that at the solution point, the y values are going to be the same. Right? The x values in both equations will be equal. The y values in both equations will be equal. So what I can do is take this definition of y equals 6x plus 7, and substitute that in for the variable. It's like I'm taking one y and just replacing it in the spot of the other. Okay? So I'm going to take this definition and I'll rewrite my second equation, 3x minus 8. And it used to say y equals 4, right? It used to say y right there. But what I'm going to do is take that y and I'm going to cut it out and I'm going to replace it with this whole expression from the first equation. I'm going to replace it with 6x plus 7. So here y equals 6x plus 7. So I took the y in the second equation and replaced it with that expression. Now I have an equation that I know how to solve. Right? I only have one kind of variable in there. It's only x. I can solve that kind of equation using the technique we've been practicing in class. So if I go through and do this, remembering to distribute my negative sign, I get minus 45x equals 60. Divide both sides by 45, and I get x equals negative 60 45ths. Both of those are divisible by 15, so I can say negative 4/3. You can see it would be hard to see negative 4/3 on a graph, but when I'm solving using algebra, it's very easy to come to this number. Remember though, my solution must have 2 points. I always have to have 2 points in my 2 values in my point. So I use this equation here to solve for x. I'm going to use this one now to go back and solve for y. I remember that y equals 6x plus 7. But I know that x equals negative 4/3, so I can substitute negative 4/3 into that value for x. And then I can solve this expression. I know those will cancel, it'll give me 2, so I'll get negative 8 plus 7. Y equals negative 1. So my solution is -4/3, -1. And of course, I can go back and substitute this into the equation. 3 times -4/3 gives me -4. Minus 8 times -1 would give me +8. So -4 plus 8 does indeed equal 4. So that is a good solution to the equation. So I'm going to go ahead and insert a page here, and let's look at the steps that we just did on the last page. First, we solved for one variable, and sometimes that's already done, right? That was already done in that case. We knew what y was to start with. Then we used that expression to substitute into the second equation. We solved for the remaining variable. Then we used that solution for the first variable. So these are the steps to use for solving by substitution. So let's go back and look at it. We solved for one variable. We got y all by itself. Then we used that expression, the solved expression, y equals, to substitute into the second equation. We took this y expression right here, and we substituted it into this one to get an equation in one variable. The remaining variable was x, so we solved for x, and then we took that value for x and substituted it back to get the value of the first variable. Here they are again. Solve for one, use that expression, solve for the remaining, and use that solution to solve for the first variable. Let's look at another example. The first thing we have to do is solve for a variable. Okay. That's already been done for me. X is all alone in this expression. It's good. Okay. I'm going to use that expression to substitute. Use that expression to substitute. So I'm going to take this x equals y plus 6 and replace the x in the second expression with it. So I will take y plus 6 plus y equals 10. Okay. I'm going to solve for the remaining variable. In this case, the remaining variable is y. It's the only one left in my equation, so I can go ahead and solve for it. Y plus 6 plus y equals 10. 2y plus 6 equals 10. 2y equals 4. Y equals 2. So I've solved for my y value. Then I'm going to use that solution, abbreviate, to solve for the first variable. I'm going to substitute again. So I'm going to take this value of y equals 2, and put it all the way back into my first expression, x equals y plus 6. But now I know that y equals 2, so x equals 2 plus 6, or x equals 8. And I have a solution with an x value and a y value. X, 8, y is 2. This should be the ordered pair for my solution. To double check it, I could come up and check my expression. 8 equals 2 plus 6. That is indeed true. And the second equation, 8 plus 2 equals 10, also good. So this is a valid solution to this system of linear equations. Following the steps. Here's one more example. This time, remember, my first step is to solve for one variable. Neither of these equations has it already done for me. So this time I have to choose one of these expressions, one of these equations to solve for. When I'm looking at these, all the variables in the second equation have a coefficient, 3 or 2. I want to choose the easiest possible solution. So I see that this y here is all by itself. So that's the equation that I'm going to choose to solve for a variable. It just takes the least work. I won't end up with any fractions. So I can move the 2x to the other side and get y equals 2x plus 3. Now I've solved an expression for one variable, get it alone. I'm going to substitute into the other equation. So I have 3x minus 2y equals 5. I'm going to use this y to replace right here. 3x minus 2 times 2x plus 3 equals 5. Remembering to distribute my sign, the whole thing, I get minus 4x minus 6 equals 5. Negative x equals 11, or x equals negative 11. I kind of took up my space. My third one is go back for the first variable. So I'm going to take this x and substitute it back in here. Y equals 2 times negative 11 plus 3. Negative 22 plus 3. Y equals negative 19. And now I have a solution. X, y. I should go back and double check that. I could get negative 19 minus 2 times negative 11 equals 3. 2 times negative 11 is negative 22. Minus a negative would give me positive. Negative 19 plus 22 equals negative 3. That's good. And I could check the second one. Negative 33 plus 38 equals 5. Also good, and this is a valid solution. So when you have to choose for which expression you're going to solve for, choose one that doesn't have coefficients, just to make the easiest substitution possible. There are some special cases that you can run into. Infinite solutions is one of them. If I went to solve this, I would get 3.5 times negative 2y plus 4. It's already been solved for a single variable. Plus 7y equals 14. This would give me negative 7y plus 14 plus 7y equals 14. You may begin to notice these are going to cancel out, and I end up with 14 equals 14, which is true and always true. So if one variable solves to all real numbers, then the solution, there's infinite solutions to the system of equations. They're going to end up being the same line. There's infinite solutions. The other special case happens when there's no solution. So if I look at this, again, y is already solved for me. So I can go ahead and substitute. I would get 3x minus 11, if I substituted in for y, minus 3x equals negative 13. You begin to see these are going to cancel, and I end up with negative 11 equals negative 13. This is the empty set. So if either variable has the empty set, then there are no solutions to the system of equations. And in this case, what happens is they're just parallel lines. No solutions to the system of equations. So we talked about the steps to solve. We identified a way to look for which variable might be the easiest to solve for. Look for no coefficients first, or for one that's easily divisible into the other coefficients. And then we talked about two special cases, infinite solutions and no solutions. So here is a concept summary that we talked about. If you have graphing, right, you just look for the variable, and you see in this case, I can't tell exactly what this variable is going to be, what the solution is going to be, so I would go back and look for substitution. I would solve for one variable. It doesn't always have to be for x. Sometimes you might solve for another. Solve for one variable, substitute back.